This is a summary of the Agentic conference I attended yesterday at Berkeley, a really interesting conference, the first one that they did, thousands of attendees, and really interesting, amazing lineup. So I'm going to start with, I'm going to go chronologically. The first session was building infrastructure for agents, Bill Daly, chief scientist, Nvidia, Ramine Roane from AMD, and Quincy Davis, founder and CEO of Foundry, the company. So I'm going to talk about what they said and how that relates to AI in general. So the idea here of the whole conference is to talk about agents. So that is, in a nutshell, a network of AIs that work together and are synchronized in one way or the other. So Bill Daly is a hardware person. He is chief scientist at Nvidia. So I guess what his job at Nvidia primarily encompasses the scientific framework in which the company operates, driving what's called Jensen's law at this point. And I think he gave a presentation that actually reminded me of one that he gave 2 years ago. So, which is maybe a little bit concerning. On the other hand, you have to also say, well, don't fix what's not broken. So he was talking about acceleration of compute and how that's driven by Moore's law, sparsity, complex instructions, and number representations. What does that mean? That means that we have an underlying process improvement of, let's say, 3x over the last 10 years through Moore's law. That's slowing down. We still have some, and there's obviously 3D, chip design and what ASML is doing. So there's still Moore's law. There's still something to be done there. Sparsity means that you can, when you do the math in the AI infrastructure, you can circumvent matrices that have a lot of zeros. So something like if it has more than 2 zeros, just don't even talk about it, things like that. Complex instructions, that is something that I believe a lot of people are doing now, that is, having a matrix multiply hard-coded in the chip so you don't have to go back and forth. Think about it this way. If we have, in the chip design world, you have an optimization problem, which is, do I want to hard-code instructions on the metal so when those instructions are given to the chip, it can execute that instruction, for example, a matrix multiply or a multiply fuse, so multiply plus add. Or should we have just add, subtract, division, like very basic things, and then have the sort of compiler software deal with those things? And I think in the world of chip design and AI, there is this trade-off, right? You have, on the one hand, you have the necessity to do very complex instructions, but they also take a lot of energy, and you might have actually a fantastic complex instruction, but you don't have enough memory to actually do the whole thing. So you might just be idle. And then on the other hand, you can have very simple instructions, but a lot of overhead on the software side, but then that could be mitigated by optimization through memory. Number representations, that is one of the key drivers actually that Daly was spoken about. So they found ways to go from 32-bit down to 4-bit. Now there's obviously a limit to that, so that's not going to continue. And I think one of the biggest positives that Nvidia has brought to the world of AI actually is the parallelism, because that is tied to CUDA. Parallelism is a very, very complex solution to the problem of compute. You can split matrix calculations and spread them over a network of GPUs. If you have the right interconnect and the right connect, since in a forward pass, for example, you depend on results from the previous pass, you have to make sure that those dependencies are taken care of. So if you take care of these things properly, and that's kind of what CUDA does, you can have massive accelerations. Another thing that NVIDIA solves is the inference problem, and the inference problem in AI world means on the data center side is the Pareto optimality between latency and how many customers you can serve. The more customers you can serve, the more money you make per watt, the more or per let's say per installed machine. And then but then you increase the latency, so you want to decrease the latency as much as you can. That problem does not exist on the edge. On the edge, you actually only have one customer, the robot, for example, or the phone. So that's a little bit different there. But then on the edge, you have massive power constraints. So that's Bill's presentation. I would say nothing new there, and that's almost a bit concerning. One has to be careful with these things. These things can signal lack of innovation, but they can also signal that there is something that is working, and that is what NVIDIA is banking on now. There's obviously no lack of competition there. I think the biggest upside of NVIDIA is the programmability and flexibility. Ramine Roane from AMD, he really said something interesting. He said you can optimize any kind of agentic AI on 3 axes: total cost of ownership, security and dependability, and user experience. I'm going to talk about security and dependability because that's the key in the second panel, actually, with Ion Stoica and Marin Zakaria and people and other people, because that's a key one, right? If you have a network of networks, and Quincy Davis, founder of Foundry, spoke about this in his presentation. He spoke about Ember, which is an open source compositional framework for agents. But that's more of on the framework side. So we have two, I think, big movements right now in agentic AI. One is Ember, maybe not as big, and the other is MCP. And MCP, which is Model Context Protocol, that's a big one. It came out of Anthropic, and that just that's the way I think about this. Model Context Protocol tries to synchronize models with tools. Like, instead of having to write bespoke code when, let's say, your Grok is communicating with, it's communicating with other tools. Even tools such as using, MATLAB or maybe accessing other websites, accessing other apps. The problem here is that there is no standardized network in terms of how to communicate with those applications. And this bespoke, the necessity to drive a bespoke code base into that agentic network is very cumbersome. MCP tries to solve that, versus what Ember is trying to solve is a different problem. That is, it's trying to build a network of networks. So, Jared compares it to PyTorch and JAX. What did PyTorch and JAX do in the 2010s? They were able to accelerate and facilitate neural network programming by, let's say, having autograd, a very simple thing. So if you think, like, people like me, and I think listeners can probably feel for that. If you were building neural nets in the early 2010s, so maybe around AlexNet or something like that, you had to specifically program a neural net, have placeholders for each. Let's say you had a neural net, and you had to have placeholders for each variable that comes in that was used to calculate the weight. Then you had to do differentiation on each of these variables, and it just was very cumbersome. PyTorch facilitated all this. It kind of became a dynamic programming tool where you just say something like forward network, and then it just takes in the data and spreads it throughout a network that dynamically grows with the data. So you didn't have to take care. You didn't have to modify each position. You could just maybe specify how big the network should be, and then it would automatically allocate data towards positions in the network, something like that. I'm not an expert, but I guess similarly, Ember is trying to do this now with a network of networks. And I think Jared, I've spoken about him, I think before, or at least I know I saw an interview with him on Twimmel. So he's out there, he's talking about Foundry, which is his company. And I think these are very important endeavors. And I think, just to summarize this first session, I guess the goal here is Build Alley is all about, of course, speed and compute, and also network connections within the data center. That's Nvidia's game. Jared Quincy Davis, he's talking more about the connection of different models. Now, why is that important? It's because inference scaling is key. And I think inference scaling is really an important concept, because you can have several models that can, think about it this way. If you have one model that you're querying, you have to overtrain the model and then over-query the model. You could have the same model used in different ways. For example, you could have the same model used in a sort of actor-critic way. So, the same model could generate several answers to a prompt and then criticize the answers by having some sort of like a discriminator and a predictor, and then vote out the best answer, for example. So something that sort of morphs towards a distributed network with voting or criticizing or something like that. So it almost reminds me of blockchain. I think this is really interesting. I'm going to talk about that a little bit more in the second installment when I talk about Ion Stoica and Marin Zakaria. But I guess I can see where this is going. Of course, Jared's PhD was with Marin Zakaria, so he is coming from this Databricks world, this distributed computing world, and distributed computing is all about standards and protocols, and also decision making in a distributed way. So kind of setting a state within the network, within a distributed network. That's a big problem. Of course, blockchain has solved that problem, and we have a similar situation here in a network of agents. Thank you.